Hello everyone, we are Group 15. For the ELEC 3300 final project, we have decided to build a smart fan. My name is Fong Kin Ho Andrew and my teammate is Hoi Ka Wong Keen. So let's go through the table of contents of our presentation. We will first walk through the objectives and key features of our project. We then will move on to the major components, such as the hardware used and the user interface. After that will be the program flow, and we will do a feature demos to illustrate our key features. We then will finish off with the future use cases for improvements and also tell you the resources that we've used. So for the objectives of this project, we aim to create a smart fan for indoor temperature control and active environment noise masking with a touch-enabled user interface for user inputs. So a little bit about our project. It is a smart fan equipped with temperature sensor, noise sensor, fan blade connected to a motor, variable resistor, a LED, and a fully functioning LCD display. For the key features are fourfold. So the first one will be the temperature detection, which we will automatically detect the temperature of the surroundings. And there will be two modes of choices, which will be the manual mode and auto mode for flexibilities and overrides for users to actually interact with the fan speed. And there goes the noise masking, which we will match the blade speed according to the environmental noises, and also a countdown timer to allow users to set countdowns and save energy. For the major components, we have decided to use a temperature sensor which gives an integer temperature value. For the sound sensor, we'll be using DF Robot's Gravity Analog Sound Sensor. And for the fan blades, we'll be using Xiaomi's mini fan connected to a motor. For the analog to digital converter ADC, we'll be using it to get users' manual inputs and also the sound sensor data. The pulse width modulation PWM will be used by the transistor to control the motor. And the variable resistor will be used to control the blade speed by adjusting R manually. So this is the user interface. Our LCD display is touch enabled, which users can actually touch the screens to switch between modes, which are off mode, auto mode, and also manual mode. It can also enable silent mode in auto, which the sound sensors will detect the environmental noises automatically and adjust the fan blade speed according to the sensor data. And the users can also set a countdown timer with K1, K2 if they want the smart fan to blow in a specific duration. So here's the program flow. There will be three modes: auto, off, and also manual. Under auto mode, there will be three aspects that will be automatically detected at all time, which will be the timer, the temperature, and also the noise. So the program will automatically detect whether a users have set a countdown and started it using K2. And it will also measure the room temperature and environmental noises at all times using the temperature sensor and noise sensor. If the users have enabled silent mode, the fan blade speed will depend on the room temperature and also the environmental noises. If it doesn't, the fan blade speed will only depend on the room temperature. For the manual mode, it allows users to tune the variable resistors and adjust the fan blade speed. If the user doesn't tune the variable resistor, the speed will depend on the initial value of VR. If it does, the fan blade speed will depend on the VR. Here's the illustration of the fan blade speed power. So there will be three levels: low, medium, and high. For low, it's between 0 and 30%. For medium, it's between 30% to 60%. And for high, it's between 60 to 90%. So there will be some temperature monitoring based on the room temperature in the auto mode. So if the room temperature is below 23%, the fan will operate between 0 and 25. If it's between 23 to 27 degrees Celsius, it will operate in 25 to 75%. And the rest will be if the room is over 27%. It's over 27 degrees Celsius. So here's some test results conducted during our experimentation. And when the temperature is 22 degrees Celsius and the noise level being 151, the speed will be approximately 15%. If it's 25 degrees Celsius and the noise level is 34, the speed will be approximately 42%. And the last one will be when the temperature is 28 degrees Celsius and the noise level being 55, it will blow at a rate of 78%. In here, we will demonstrate the key functions in our smart fan, which are the temperature control, countdown timer, and also the active noise reduction based on the background noises. Here's the feature demonstration of our smart fan project. After the touch calibration, users are logged into our system and you can see the user interface. The noise level is rapidly changing because of our noise sensor. And when we snap our finger very close to the noise sensor, it signals a massive jump. We can also lightly tap on the microphone to see whether the noise level changes. So here comes the two modes, which is auto mode and manual mode. We can tap on auto to automatically turn on the fan immediately. We can also choose manual mode and the LED will light up, signaling that the users can manually override and interact with the speed of the fan by tuning the variable resistor. Here's another view. And when the users tap on silent mode, the speed will automatically decrease so that there will be less noise generated by the fan blades. The users can also set a countdown timer using K1 and K2. For K1, it will be used to control the units of the time, for example the hours, the minutes. And we can start timer using K2. So let's set the timer for 2 hours and 1 minute. So after waiting for 2 hours, you can see that the timer approaches to 0 and the fan will automatically shut down. So that's it for our demonstration. For the future use cases, because of the budget constraints, the effects of temperature control and noise masking are limited due to the lack of temperature sensors and noise sensors. However, the scope of the project can actually be extended to help light sleepers to provide a more comfortable experience and noise-free environment with the auto mode on and countdown timer to save energy in long run. And here's the list of resources and hardwares that we have used in our project. So that's pretty much it for our presentation. Thank you for listening, and we now open the floor for questions.